Hey guys, let's dive into chapter 11. It's called the Chi-Square Distribution. This will be a brand new way to perform hypothesis tests. It's really fun. You also notice that chapter 11 is very short. The lecture is only 2 pages, in fact, because we've really done all of the big work with hypothesis testing up until now. So we can learn a new style and just dive right into it. When you read the chi-square distribution, that might look a little intimidating. Where does that name come from? What is this all about? Okay, we're going to explain all those things, of course. So I'll just start reading there at the top of the lecture document. It says, this distribution allows us to conduct hypothesis tests in other types of situations. The sort of things we've seen before, right? They involve like sample means and standard deviations, or maybe sample proportions of success. That's not the way the chi-square distribution will work. It's a whole new approach. So let me read you quickly just these two examples of questions somebody might ask. Do employees call in sick equally throughout the work week? Right, maybe an employer is curious about their employees and they'd like to know. Sometimes employees tend to call out more on Mondays or Fridays, right? So we'll be able to look at that with the chi-square distribution. Or maybe that second one, is a college student's anxiety level related to their overall GPA? If two things are related, you can study you can study right, to perform a hypothesis test to see if two things can be shown to be related or not. Okay, so let's begin with the goodness of fit test. So it turns out in the chi-square there are two different styles. We call them the goodness of fit, and then the other one, if you scroll down to about the middle of the second page, it's the test of independence. But okay, let's see where this begins. The goodness of fit test. This test will decide whether or not observed data fits a particular distribution. For instance, it may seem like a population parameter would fit a uniform distribution. Now, what would be an example of where you might assume that something would fit a uniform distribution? That's actually the first example above. Do employees call in sick equally? You would think the chances of getting sick, it doesn't matter what day it is, all days are, should be equal. When people get sick, and maybe that's true, maybe it's not, right? So it seems like a population parameter would fit a uniform distribution. A test is needed to help confirm your suspicions or to reveal otherwise. And as you might expect, we've got a whole new way to calculate the test statistic, and this is actually where the name chi-square comes from. So it says the test statistic is found by, and you see that symbol there on the left. I'll just draw it here. It looks like a capital X, but it's actually not. That is the Greek letter chi, and it's got this kind of like, curvy sort of arm here and then straight down. And then we put a square on it, chi. We put a square on it, and that's where we get the name chi-square. So notice the formula for that. We've got the summation symbol, the sigma, right? So that's going to be telling us to add up a bunch of numbers. We'll see that here in a little bit. And then notice the formula: observed minus expected squared divided by expected. Okay, so that'll make sense. Once we see an example, we'll have observed data and we'll have expected data. If you look below, it says in calculating the p-value, the degrees of freedom. Okay, there is a degrees of freedom when it comes to the chi-square, and it's the number of categories minus 1. What are the categories? Okay, well, we're going to see that right now. We're going to jump into practice number 1, and I'll just advise you, have your StatCrunch up and ready as well, because we're going to use that to calculate our p-value, just like in the other tests. Okay, practice number one. We're going to go to that employer with the sick days. An employer of a large company wants to know if his employees call in sick more frequently on certain weekdays. He wants to believe employees are sick equally throughout the week. It makes sense, like that's what his assumption will be. Over 60 weeks, that's a long time, right? That's over a year. Over 60 weeks, the employer notes the day that most employees call in sick. Okay, so that's kind of seems strange for a moment. The employer notes the day where most people call in sick. So he's not noting every sick person. He's just saying what was the most popular day to be sick, and we like give that a tally for that week. Okay, so we get the data right there. So Monday, Tuesday, Wednesday, Thursday, Friday. 14 times Monday was the most popular day to be sick that week. All right, 10 times it was Tuesday. Most people called in sick on Tuesday. And it kind of diminishes, right? Wednesday is only 8 times out of the 60 weeks. Thursday, 12 times out of the 60 weeks. And Friday, 16 times out of 60. Friday was the most popular day to be sick. Okay, maybe not all that surprising. Mondays and Fridays a little higher. Conduct a hypothesis test to decide if the number of days that most employees call in sick occur with equal frequency, and we'll use alpha equals 0.05. Okay, how are we going to begin this? So we're going to walk through all of the steps. It's the same 5 steps we've always done, right? Step 1, state the null and alternative hypotheses. Step 2, calculate the test statistic. Step 3, find the p-value. Step 4, compare the p-value to the significance level. And step 5, decide to reject or fail to reject the null hypothesis. Okay, so let's see how this works. What are we going to do for the null and alternative hypothesis here? Okay, so remember the null hypothesis is your assumption. And it says in the problem, he wants to believe employees are sick equally throughout the week. Okay, so this is one way you might say it. So I've got, let me see if I can focus slightly better. Maybe. All right, so practice number 1. Step 1, the null hypothesis. When it comes to the chi-square, there's not a simple kind of mathematical way to do it. We just have to write it out in words. Okay, so the null hypothesis here, the way I phrased it works. Sick days occur with equal frequency. People are sick equally throughout the week. You could phrase that differently. You could phrase it exactly the same way the problem says it. Right, the problem says it as employees are sick equally throughout the week. You could just copy that language. That would be great. I phrased it a little differently here. There's some flexibility. At the end of the day, you just want to be clear. The sick days are spread equally throughout. Okay. So then what's the alternative hypothesis? Right, and this type of hypothesis test is very different from the other ones. When it comes to the alternative hypothesis, you just need to negate the null hypothesis. So we're going to say sick days, we're kind of putting sick in quotes, right? Sick days do not occur with equal frequency, and the key there is the not. And that's how the chi-square hypothesis test is always going to work. You got your assumption, and then your alternative is simply negating it. And usually you can negate it with the word not, in the statement at the appropriate location. So sick days do not occur with equal frequency. You might say something like sick days occur with different frequencies, for the different days of the week. But usually the simplest way to state this is just with the word not. Okay, so we've got our null and alternative hypotheses here. Let's go to step 2, write the test statistic. So it turns out to calculate these test statistics, it takes a little bit of work. And then we're gonna crunch some numbers, and then we're gonna add them up. So right here, I've just repeated that formula. Step 2, I've got my chi-square equals, and notice, I drew the summation, the sigma. Where you see observed, you can just write an O, and where you see expected, write an E. So observed minus expected squared over expected. Okay. Now, what do we even do with that? So here's what we can do. That table that is provided for us in the problem, those are the observed, that's the observed data. Okay, so the table that is given, that's the observed. Let's say observed data. Okay, so those will all, that 14, 10, 8, 12, 16, those will all go in for the O. And I think that's what I've got here. Monday, Tuesday, Wednesday, Thursday, Friday. I've got O for observed, and then I filled in those numbers. We're going to create a table, and that's going to help us do our calculation. Okay, let me go ahead and scroll this up. So you're going to see this table unfold. Now, if what they give us in the table is the observed, maybe it'd be easier to write like OB, right? Observed. Then what is the expected? The expected is based on our assumption in the null hypothesis. We assume, or we expect, that sick days occur with equal frequency. So let me show you what that row would look like and just where that comes from. So the expected, maybe EX is easier. The expected would all be 12s. Why would the expected here be all 12s? You would think, well, there were 60 weeks, right, that they measured data, and there are 5 days of the week. So if all the days of the week people are getting sick with equal frequency over 60 weeks, then take 60 and divide by 5 to get 12. So we would expect that each day of the week was the most popular day to be sick, the same number of times as any other week, right? So if they each got a 12, then that's kind of like, if getting sick really is random, then each of the 5 days should share the same number. And if there were 60 weeks, right, so then 60 divided by 5, each would get a 12. And you can see the uniform distribution right there, right? All of them have a 12. Doesn't matter which day it is. Okay. We'd say, all right, we've got our observed, we've got our expected. What do we do now? Okay, for each pair, we're going to do this calculation. Okay. So my next line, I've got observed minus expected squared divided by expected. So how do I fill these in? Well, I just take the two numbers. So for that first column, right, 14 and 12, so I'm going to say observed minus expected squared divided by expected. 14 minus 12 squared over 12. And that turns out to be 0.3333. That's 1/3. If you did it as a fraction, I can actually convert in this calculator F double arrow D. I could convert to a fraction there, which is pretty nifty. If you wanted to use decimal places and round it, maybe like 4 decimal places or so, 0.3333, that would be totally fine as well. Here, I decided to go with the fraction because it's so nice. But you could use a decimal place there as well. If you do, I suggest 4 places, so you don't have any rounding inaccuracies later. Okay, so we're going to do that same procedure. We're going to use that formula for each of our columns. Okay, so when I come to the next column, 10 and 12, then I'll say 10 minus 12 with parentheses squared divided by 12, right? Always observed minus expected, with the parentheses squared divided by that expected, which again is 12. And well, it happens to be in this case, I got 1/3 again. If you do it for 8 and 12, you wind up with 4/3, or again, you could use the decimal place. When they are both 12, notice that. On Thursday, both are 12. Well, what's going to happen? Observed minus expected is going to be 0. So that's going to end up being 0. And then Friday, we get 4/3 again. Okay, so do that calculation for each of the 5 days. Then what? Now that's where the sigma comes in. We're going to add all of those together. Okay, so 1/3 plus 1/3 plus 4/3 plus 0 plus 4/3. Here it's kind of nice if you did it in the fractions because they all have, a denominator of 3. So you could just add numerators. 1 plus 1 plus 4 plus 4 is 10/3. Or if you rounded it, you're probably going to get the same test statistic as I got, 3.33. So that's our test statistic right there. Whatever that number was, that's what chi-squared equals. I like to round that to 2 decimal places. And so there we go. Okay, very nice. Now at this point, once we have our test statistic, chi-squared equals 3.33 here, well, now we go to find the p-value. So you would need your StatCrunch calculator. I can't really bring it up on the screen at the same time as I'm recording this, but if you go there into StatCrunch and bring up the calculator, you will see a chi-square option. So open up that chi-square calculator. It's going to work very much like the other calculators. You'll see the basic shape of the chi-square. If I could just speak to it as you're looking at it now, hopefully, it kind of looks like a bell curve. Actually, I can probably kind of draw it down here. It kind of looks like a bell curve, except it's like off-centered. It's pushed more to the left. So it kind of does this sort of thing. So it kind of almost does this bell curve shape, but then it gets stretched out this way. All right. And there's 0. So the bell curve, right, goes back this way and forward that way equally, right? Here's where the bell curve would do. So it's kind of got a bell shape, but it stops at 0. It does not go negative, and it extends sort of this way and gets stretched out, like skewed to the right. Anyway, okay, so you're looking at something like that. So what does that mean for calculating our test statistic? Or calculating our p-value, I should say. So our p-value, when you see it there, couple things. So it's the probability that chi-square, and then we'll put in our 3.33, right? We don't have to change anything else when calculating this. And here's something that's really, really, really nice. The symbol between them. Now you have the option to do a greater than or a less than. But when we do our hypothesis test and our p-values, it's always a greater than. When you do the chi-square hypothesis test, it's always a greater than. And that is really, really a relief for a lot of people. You don't have to think about that. It's always a greater than. Why? Why is it always a greater than? Because when you calculate your chi-square, your test statistic, that's always going to be positive. Always. This is always going to be a positive number. Why? Because it's based on a square, and squares are always positive. So you'll always have a positive test statistic, which means this will always be a greater than. Every time. Okay, now you also need to be careful about your degrees of freedom. What is our degrees of freedom? I see I don't have it written down. Oh, wait, I do. I have this at the bottom. Use the StatCrunch chi-square. Okay, that's important. What is our degrees of freedom? Okay, so in the lecture it says it's the number of categories minus 1. Well, how many categories do we have in this problem? And you can see the number there, but what are the categories? The categories are the days of the week: Monday, Tuesday, Wednesday, Thursday, Friday. We've got 5 categories. So we're going to use degrees of freedom 5 minus 1, or 4. So put the 4 in to that calculator, as well as degrees of freedom. You got to change that, and then greater than 3.33, and you should get a number like this. I believe I rounded mine to 4 decimal places. So that's my p-value right there, 0.5042. Okay, hopefully you can recreate these numbers in that calculator. I'm going to go on. Step 4 is to compare that p-value with the significance level alpha. Well, they told us alpha in this problem is 0.05. Which one is bigger, 0.5042 or 0.05? Clearly the p-value is much bigger in this problem. So the p-value is the larger. And now if you remember, if your p-value is the bigger, does that mean you reject or fail to reject the null hypothesis? If the p-value is bigger, we fail to reject the null hypothesis. This is not enough evidence at all. Not even close. Not even close. You know what? Just looking at that table right at the beginning, I actually felt, like we had some data that pointed to these days people are not calling in sick equally when you look at that table. But it turns out when you do the test, that's not enough evidence. I agree it's some evidence, but not nearly enough. What's happening with the graph? Sometimes we like to graph these things in shade. What just happened? So 0.05 would be the upper 5%, right? Whatever this is way up here at the top. 0.05. Our p-value landed at 0.5, so that's like 50%. So that's like way back. I mean, that's our p-value. Not even close to that shaded region. I mean, so you're thinking like almost just about 50% is on the left and 50% is on the right. I mean, nowhere. I think this should actually be quite a bit further this direction for a better drawing, something like that. Not even close. Okay. While we're at it, let's go ahead and give the interpretation of our the results of our hypothesis test, right? So because we fail to reject, we'll say there is not enough evidence. And then what? Well, just, speak to, your alternative hypothesis here. There is not enough evidence that sick days do not occur with equal frequency. So I'm just repeating the language from my alternative hypothesis there and saying there's not enough evidence for that. There is not enough evidence that sick days do not occur, kind of a double negative, but that's all right, do not occur with equal frequency. There you go. Okay, I hope you enjoyed that first example. We're going to get to practice number 2 next.